All right, welcome back. Continuing on with thermodynamics. We've talked about entropy. We've talked about entropy changes in the universe, entropy changes in the surroundings, entropy changes in the system. And the last thing we talked about was how do we determine the entropy changes in the surroundings based on enthalpy. And then when we add the entropy change of the surroundings to the entropy change of the system, uh, does the entropy change of the universe increase? And if it does, then we have a spontaneous reaction. So in this section, instead of doing all of those different steps, we're going to combine those into a new term called Gibbs free energy. So Gibbs free energy will help us determine whether a reaction is spontaneous or not in one equation instead of multiple steps. We're also going to talk about standard free energy changes. So those are under specific conditions, and we'll talk about those specific conditions. And then we're going to use delta G and standard Gibbs free energy to solve problems. So this is probably the most important section of this chapter, but you have to understand the previous sections on enthalpy and entropy in order to understand this section. So it is important. It is the most important section, and we will use this section in the next chapter. But again, you have to understand entropy in order to do this. So here we have what we talked about before, that the change in entropy of the universe is equal to the change in entropy of the system plus the change in entropy of the surroundings. And we know the value is greater than zero because we assume the universe will keep expanding, that the number of positions available for energy to be dispersed within the universe is still increasing, and so that's why the value should be greater than zero. So in the previous lecture, we learned that if we substitute delta H of negative delta H of the system divided by T for the surroundings, we substitute that in for this, we get this equation. And then we want to get rid of the denominator, so we multiply everything by T here, the temperature, and we get this equation. And then nobody likes this negative delta H, so we're going to multiply everything by negative 1, and we get this equation. So here's what we have. Negative the temperature times the change in entropy of the universe is equal to the change in enthalpy of the system minus T times the change in entropy of the system. And because we multiplied this by negative 1, notice that it changed the value of the equality there. So now we have that as less than. All right, so let's look at the next slide. The next slide is what happens when we simplify this and give us this new symbol. So what we have here is this becomes delta G, or this becomes G and then delta G. And again, we can't measure G or enthalpy directly because we're inside the universe. All we can measure is changes. So this is theoretical, and then this is the final equation here. Delta G equals delta H minus T delta S. And then you say, why do we need to know this? Because now we're focused on the system's entropy and the system's enthalpy. So what we learn from this is that if delta G is negative or less than zero, we have a reaction that will be spontaneous in the forward direction and non-spontaneous in the reverse direction. So think of it both ways. If delta G is less than zero, that means it's going to be a negative value. The reaction is spontaneous in the forward direction and non-spontaneous in the reverse direction. If delta G comes out to be greater than zero, then the reaction is non-spontaneous in the forward direction. It is spontaneous in the reverse direction. And if you happen to choose terms that make, or values that make delta G equal to zero, the system's at equilibrium. So you're saying, give me an example of this. Well, think about your car battery. So your car battery has a chemical reaction happening within it. It generates electrons. The electrons, when you turn the ignition key, that creates a circuit. The electrons flow out of the battery, crank the starter, which then cranks the engine, gets the engine going. That's a spontaneous reaction. All you have to do is turn on make the connection by flipping the ignition switch, and it instantly happens. It's spontaneous. Now, when you turn the ignition of a dead battery, what has happened is, a lot of people think it's delta G is greater than 0. No, it is delta G equal to 0. The battery has come to equilibrium, and therefore the reaction is not going to generate enough electrons to crank the starter to crank the engine. It's still, so think about it. What we're looking at is the reaction spontaneous in the forward direction. That means it's non-spontaneous in the reverse direction for this reaction. And for the other one, it's spontaneous in the reverse direction, but it's non-spontaneous in the forward direction. But for our battery, we want spontaneity both ways, right? We want to be able to discharge the battery and crank the engine. And then we hope that the alternator in the engine will force electrons back through the battery, which is a separate process, but it forces to recharge the battery so that we can keep having this cyclical process of recharging the battery, discharging the battery to form to crank the engine. So that's what we're looking at. But what I want you to get out of this is really important. Delta G less than 0 spontaneous in the forward direction. Delta G greater than 0, meaning a positive value, non-spontaneous in the forward direction. And again, if you get delta G equals 0, then you are at equilibrium. So this table is really important. So how you're going to use this table is you're going to write the equation delta G equals delta H minus T delta S. And what we want to know is, given the values of delta H and delta S, is the reaction going to be spontaneous in the forward direction or not? So here's what we have. If it's an exothermic reaction, which means delta H is negative, and it's a positive entropy change, remember T is an absolute value. We're talking about Kelvin, and it's either 0 Kelvin or some positive value. So this is always going to be a positive value here, unless it's 0 Kelvin. So a negative times a positive is always a negative. So when you have an entropy change that is positive, you're going to get an overall negative value for this. So a negative for the delta H and a negative for all of this means delta G is always negative, and that reaction is always spontaneous in the forward direction. So that's what you're going to be doing, and I want you to spend some time on this slide plugging in some positives and negatives and seeing what happens, because you have to get this slide down. You have to get the process down. So let's look at the next one. If it's an endothermic reaction, means requires energy for the reaction to happen, and the entropy decreases, that means it gets more orderly, not as much disorder. Then what you have is you have a negative, this is a negative now, times the positive on the energy gives you a negative, and then a negative times this negative here gives you an overall negative value, gives you overall a negative value here, or positive value. Let's see. Let me think that again. Negative and a positive is a negative. Yeah, and negative times a negative gives this an overall positive value. So if we add these together, delta G will always be positive, and so it'll always be non-spontaneous in the forward direction. So those are the two extremes, right? If it's exothermic and it increases entropy, it's always spontaneous. If it's endothermic and it decreases entropy, it's always non-spontaneous. Delta G will always be positive. Most students get that, don't see much problem with it. Here's where students get into problems, these last two conditions. I want you to think about this one right here. H2O liquid becomes H2O solid, so we're freezing water. Water does not freeze spontaneously above 0 degrees Celsius. So it's spontaneous at low temperatures and it's non-spontaneous at high temperatures. So what's going on here is we have a delta H that is negative, because when a liquid goes to a solid, it releases heat. All right. And then we have a T, we have a T minus T delta S, and we know solids have less entropy than liquids, so this is going to be a negative entropy change here. We know the temperature is always positive. So what we're looking at is this whole thing here, minus T delta S. If this term is larger and dominates over this negative value for delta H, then the reaction is going to be spontaneous. So when is this temperature larger? When is this overall term larger? It's when the temperature increases. So above 0 degrees Celsius, this reaction is non-spontaneous, and above 0 degrees Celsius, this reaction, oops, did I do that incorrectly? Negative exothermic, and then this is negative, and non-spontaneous at high temperatures. Oh yeah, so we're going from a liquid to a solid. So if this gets larger, right, this term overall dominates, which is positive, because a negative times a positive is a negative. A negative times a negative then makes this a positive. So this term dominates at high temperatures, and this reaction is non-spontaneous. All right. At low temperatures, this term is less positive. It's still positive, but it's less of a value than this negative value here. This term dominates at low temperatures, and delta G will be negative, and therefore it will be spontaneous. So negative it's an exothermic reaction which increases order or decreases entropy. This only can be spontaneous at low temperatures, like the freezing of water. All right, so then the other case scenario is where the reaction's endothermic. That means it takes energy for this reaction to happen, but you see an increase in entropy. So here, again, it's negative T delta S. This is always positive. So positive entropy change and a positive temperature, positive times the negative here, makes this an overall negative term. And if this term dominates over this endothermic process, when does that occur? When temperatures are high. So at high temperatures, this reaction becomes spontaneous because overall this term dominates, which is a negative term here. So again, positive times the positive temperature change times the negative here makes this overall term negative. And that's what we want, because delta G that is less than 0 is spontaneous. So this would occur at high temperatures. And the example they give is, they could have said H2O solid going to H2O liquid. They used mercury 2 oxide going to mercury liquid. That's fine too. I wish they would have just said like something like H2O. How about H2O liquid going to H2O gas? That reaction becomes spontaneous at high temperatures. So spend the time on this slide. I think this is the most important slide as far as kind of condensing information together for you to be able to determine spontaneity. And this can be done without, the first two can be done without really doing a calculation. The second two, you are going to have to calculate it. You're going to have to determine, is the T delta S term large enough or small enough to affect the overall delta G? So here's how the problems look. It says, according to table 18.4, a reaction will be spontaneous only at high temperature if both delta H and delta S are positive. So what I want you to think about, if this is positive, it's endothermic, but we are seeing an increase in entropy, and those reactions only become spontaneous at high temperatures. And if you're having problems with this, what I would tell you to do is to write something like H2O liquid going to H2O gas. It takes energy to make a liquid turn to a gas, so that's a positive value for this, but gases have an increase in entropy over liquids. So that's what we're looking at. So they tell you what the delta H for the reaction is, and they tell you what the delta S for the reaction is. Now, here's the most common mistakes on this problem. First of all, this temperature has to be converted to Kelvin. Why? Because these delta H's and delta S's are in Kelvin, not degrees Celsius. And then the most common mistake is this. If we're going to add these together into the equation, delta G equals delta H minus T delta S, or subtract them if you want to do that, the difference. These units have to be the same. You can't subtract or add units that are different. So delta H is in kilojoules per mole, and delta S's are in joules per Kelvin mole, but you're going to multiply by the temperature in Kelvin here, so that will make it in kilojoules per mole as well. So you have to convert. This is the number one mistake right here. You either have to convert the delta S into kilojoules per mole, or you have to convert the delta H into joules per mole. But one of those has to be done. Typically what is done is the delta S is generally calculated into kilojoules per mole, and the reason why is delta G's are in generally kilojoules per mole. So that's generally what you do, and that's what they're doing here. They're taking the delta S for the reaction, and we're going to convert the joules to kilojoules. So 10 to the third joules is a kilojoule, and there's my answer in kilojoules per Kelvin mole. So now once I do that, I'm ready to plug it into the equation, and they actually use this equation to find, they're trying to find out what temperature, I guess I read that incorrectly, they're trying to find out what temperature does this become spontaneous. So what they're doing is they're saying delta G equals delta H minus T delta S. At equilibrium, delta G equals 0. All right, at equilibrium, this equals 0. So we have 0 equals delta H minus T delta S. And we're going to solve for temperature. So we get temperature equals, we move this over, we get, let's see, we get delta H. If we solve for this, we're going to get, for T, we get delta H over delta S, and the negatives cancel out. All right, so that's what they do. They plug it in here. Both of these are in kilojoules per mole. So the kilojoules cancel out, the moles cancel out, the Kelvin's in the quotient of a quotient. It pops up here, it's 419. So 419, if we convert that to degrees Celsius, is 146. So that's what the temperature is at equilibrium. Let's go back to the question, though. Let's go back to the question. For the reaction, and they tell us that, determine the temperature above which the reaction is spontaneous. Okay, so they're helping you out here. So this reaction only becomes spontaneous at high temperatures. So if it's positive for delta H and it's positive for delta S, these reactions only become spontaneous at high temperatures. And again, you go, how do I know that? Because you've got this table down which says that right here. If they're both positive, this reaction only becomes spontaneous at high temperatures, all right? So that's why this table is so important. We're going to be referring to it over and over. So they're helping you out here. They're saying at what to find the temperature, and they're already helping you. They're saying above which the reaction is spontaneous. So be careful on these problems, because if they don't tell you above, you're going to have to go back to the table and say above this temperature. So this temperature that you just calculated is the equilibrium temperature. It was where delta G equals 0. And then we're solving for T. Because this is a positive delta H and a positive delta S, these reactions only become spontaneous above this temperature. So anything above 146 degrees Celsius is going to be spontaneous. I hope that makes sense. But that's what you have to do. Like, had these both been negative and you came up with this value, then you would say below this temperature, they're spontaneous. And again, let's go back to that. Let's go back to the table. That's why the table is so important. So when delta H is negative and delta S is negative, it's only spontaneous at low temperature. So the temperature you calculated is the equilibrium temperature, and you would say below that temperature it's spontaneous. So that's why this table is very important. All right, let's move on. So the next one is standard free energy changes. And so what's different here is you got the not symbol. So that not symbol means something. So there's delta G, non-standard conditions, and then there's delta G naught, standard conditions. So what are those standard conditions? Everything has to be in their standard states when you're calculating a standard Gibbs free energy. So here's what it has to be. If it's a gas, it has to be at 1 atmosphere pressure. If it's a liquid, it has to be a pure liquid. If it's a solid, it has to be a pure solid. It's not aqueous or something like that. If it is aqueous, it's a 1 molar concentration, all right, if it's a solution. And then here's where it gets to be a little crazy. If it's an element, it has to be at 1 atmosphere and 25 degrees Celsius. Why 25 degrees Celsius? Because that's 298 Kelvin, and that's what we assume is standard room temperature. So take some time on this slide. I find students have problems sometimes with distinguishing between delta G and delta G naught. If it's delta G naught, it has to follow this form. It has to be meeting these statements that we have below. And if it doesn't, then it's just Gibbs free energy change, not standard Gibbs free energy change. They are different, and we'll see the relationship here in a minute. All right, so how do we calculate standard Gibbs free energy? Well, you've seen this equation over and over. We've calculated in chapter 5, we calculated standard enthalpy. In the beginning of this chapter, we calculated standard entropy. And now we have the same thing, standard Gibbs free energy. You look in the appendix in the back of the book, you do the products minus the reactants, and that's what we have here. And you find the standard Gibbs free energy of formation for each reactant and each product. Do the products first times their molar coefficients, and then subtract from that the reactants and the Gibbs free energy of formation, standard Gibbs free energy of formation for each of those reactants multiplied by their respective coefficients. This can be condensed down to this equation to make it more writable. And I mean, we've seen this over and over. This is called the direct method of calculating the standard Gibbs free energy. Okay. So we assume that there's 1 mole compound. It's synthesized from its constituent elements in their standard states. Just like these were the same assumptions that we made when we calculated delta H naught back in chapter 5. So we assume standard Gibbs free energy of formation. The F here is important. Formation is that we are doing this. We're taking hydrogen. Its standard state at room temperature is diatomic. It's a gas. We're taking a 1/2 mole of oxygen gas, and we're forming 1 mole of water in its standard state at 25 degrees Celsius, which is a liquid. So the Gibbs free energy of this and this, the standard Gibbs free energy of formation for hydrogen and oxygen would be 0. The standard enthalpy of formation for both of these would be 0. Now the entropies are going to have values here. Because remember, the only way you get an entropy of 0 is a perfect crystalline solid at 0 Kelvin. So just remember, formation means, it's just like, and again, maybe you forgot, but it means this specifically, that a compound is synthesized from its constituent elements in their standard states. And you get that from the periodic table. All right, so here we have a problem. Here they want to calculate what the standard Gibbs free energy for this reaction is. So we have carbon graphite, which that's the standard state of carbon at room temperature, not diamond, reacts with oxygen to form carbon dioxide. And we'd like to know what this reaction is going to be. So we look up standard Gibbs energy of formation for carbon dioxide gas in the back of the appendix. That's our product. Minus the reactants, the standard Gibbs free energy of formation of carbon, graphite, and the standard Gibbs free energy of formation for oxygen gas. Well, these are the standard states for carbon and oxygen. So their standard Gibbs free energy of formation for both the carbon, graphite, and the oxygen is 0. So all we need to know is what is the standard Gibbs free energy of formation of the carbon dioxide, which you look in the table. So that's just showing you that this is the definition of Gibbs standard free and Gibbs standard free energy of formation, that you take the elements in their standard states and you make 1 mole of product. And you can think of this, and so that's what they proved here, is that the standard Gibbs energy, free energy of reaction is the same as standard Gibbs free energy of formation. In this case, they mean the same thing, because we made 1 mole of this from its constituent elements in their standard states. All right, so on the problem here, we'll do one of them. These aren't going to be standard Gibbs free energy of formations, right? Because this is the standard state of this element, but this isn't an element, this is not an element, this is not an element. The only thing that's going to have a standard Gibbs free energy of formation of 0 is the oxygen. So the standard Gibbs free energy of formation for O2 is 0, because that's its natural state at 25 degrees Celsius. All right, and the rest of these you're going to have to look up in a table. So they do that for you. They say that methane is this, and they say carbon dioxide is this, and they say oxygen or water liquid is that. Okay, so we're ready to solve the problem. So let's look at it. So it's products minus reactants. So it's the carbon dioxide times the water minus the methane times the oxygen. We've looked these up in the table. Here it is for the carbon dioxide. We had 2 moles of water formed, so that's why there's a 2 here, times the standard Gibbs free energy of formation for water, minus the standard Gibbs free energy of formation for the methane. And again, here's the oxygen. That is its standard state. That's why it's 0. Make sure, I can't stress enough, you calculate what's in this bracket, then you calculate what's in this bracket, and you subtract bracket 1 from bracket 2, and you should get that number there. All right? So try that on your calculator. Make sure you're getting that number. And then this is what you should know. Is this reaction spontaneous or non-spontaneous at 25 degrees Celsius or 298 Kelvin? And your answer should be it's spontaneous because it's a negative value. It's a negative value here. Negative value for delta G means spontaneous. We're not going to do the other one. I'll let you do that one if you want to try it. Okay, so this next thing is to show the relationship between delta G, non-standard conditions, and the very restrictive standard Gibbs free energy. So the first thing we do, so what we're looking at here is delta G naught equals delta H naught minus T delta S naught. Okay? So because these are not symbols, we can go to the appendix and find the standard enthalpy of formations for our products and our reactants. And we can calculate the standard enthalpy of this reaction. We can do the same thing for entropy, products minus the reactants, find those in the table, and we can calculate the standard entropy change for this reaction. And then we can plug those into this equation. And when we do that, we would calculate the standard Gibbs free energy for this reaction. And because it's a positive value, a large positive value, we know this reaction does not favor product formation, that it doesn't favor it. It's not likely to go spontaneous in the forward direction. All right? At 25 degrees Celsius, at 25 degrees Celsius, at standard conditions. Well, when does it become favorable? All right, so let's look at this. When delta G naught is equal to 0, we're at equilibrium. We're at equilibrium. We solve for T, we get this, and so this is the temperature at equilibrium. So a temperature, and again, what are we looking at here? We're looking at a positive entropy. Let's see, let's go back. let me go back. Yeah, we're looking at a positive enthalpy change and a positive entropy change. This becomes spontaneous above this temperature. That's what this is saying here. Because we saw in that table, that's really important to understand, this is an endothermic reaction with an increase in entropy. When does this reaction become spontaneous? At higher temperatures. We can actually solve for the temperature here by setting this equal to 0, which is equilibrium. Solve for that temperature and then realize if this is positive and this is positive, above that temperature, the reaction becomes spontaneous. So above 1108 Kelvin, or 835 degrees Celsius, this term dominates over this term, and this is a positive times the positive temperature times the negative. This overall term becomes negative. This overall negative dominates over the positive here, which makes delta G negative, and the reaction is spontaneous. So at high temperatures, this reaction becomes spontaneous. Now, I'm going to say, I'm talking about this, I'm trying to stress this really, this is the most important part of delta G right here, is being able to think about this, that if these are both positive values for entropy and enthalpy, then more than likely at low temperatures, this is going to be non-spontaneous. It's not going, because you're going to get a delta G value that is positive. But if this term dominates, and when does it dominate? When this temperature gets high, then this term, again, a positive entropy, positive temperature times a negative makes this overall negative. This term dominates and delta G is less than 0. At what temperature does that happen? Oh, that's why we solve for it. We set this equal to 0, which is at equilibrium. And then we have to know if this is positive and this is positive, then higher temperatures, a temperature above this equilibrium temperature, is when it becomes spontaneous. There's a lot of questions tied to that table, and then knowing the general equation, delta G naught equals delta H naught minus T delta S naught. Or you can say delta G equals delta H minus T delta S. Again, when you go outside the naught symbols, though, these have to be given. The naught symbols mean, yeah, you can calculate it through the direct method of the summation of the products minus the summation of the reactants. So that's where we're going with this. This is all kind of coming together into a few equations. All right, so let's look at this. It says at the temperature at which a phase change occurs, like a melting point or boiling point, the system's at equilibrium. All right, delta G equals 0. And then we can solve for either delta T, we can solve for T or delta S. That's what they did here. So the entropy of ice going to water, that entropy is 22 joules per Kelvin mole. And then the reverse of that, water going back to ice, that's more organized, right? Less disorder. It's a negative 22.0 joules per Kelvin mole. So that's what they're showing here, is that if the forward process is a positive change of 22 joules per Kelvin mole, then the reverse process has to be a negative 22 joules per Kelvin mole. All right, so let's read this problem. The molar heats of fusion, which is the melting of the ice, and the vaporization of benzene are 10.9 and 31.0 kilojoules per mole, respectively. Calculate the entropy changes for the solid to liquid and liquid to vapor transitions for benzene. So what we're talking about is we're going from a solid to a liquid, and then we're going from a liquid to a gas. Fusion deals with this, vaporization deals with that. Assume 1 atmosphere pressure, benzene melts at 5.5 degrees Celsius and boils at 80.1 degrees Celsius. So the first thing we have to do is, everything we're dealing here is in Kelvin, so we got to convert both of those temperatures to Kelvin. Okay, and then we're going to calculate the delta S of fusion. So we're given the delta H of fusion in the problem, divided by the melting point, which is this. And that gives us an entropy of 39.1 kilojoules per Kelvin mole. Or it's kilojoules per Kelvin mole, but you know, entropies are in joules per Kelvin mole, so that's why they did that. Do the same thing for vaporization. Notice this number is larger. Yeah, it takes more energy to convert a liquid to a gas than it does a solid to a liquid. And the temperature is higher. And we calculate that out, and the delta S of vaporization, the entropy change of vaporization is 87.7. Again, notice this is a larger number. Absolutely. There's a lot more entropy in a gas than a liquid. That transition is greater than a solid going to a liquid. Because liquid and solid, they're condensed phases. The molecules are fairly close together compared to a gas. All right, so here is the two big components that we're going to apply what we've just learned. And I'm going to stop here. I'm going to make another video because I want to focus on this. So what we've done here up to this point is we defined entropy, delta S. We looked at the relationship between delta S of the surroundings and the enthalpy, the delta H of the system. And then we have come up with a new term called Gibbs free energy, which takes into account delta H of the system and delta S of the system. To calculate Gibbs free energy, we found out that if Gibbs free energy changes are less than 0, the reaction is spontaneous. If Gibbs free energy changes are greater than 0, it's non-spontaneous in the forward direction. And if it just so happens delta G equals 0, we've chosen values that are at equilibrium. We've used that equation, we've used this equation to determine whether the reaction is spontaneous or not. And this can be either standard conditions or non-standard conditions. If they're standard conditions, you can calculate these using the appendix in the back of the book. You can calculate the delta H standard conditions. You can calculate the delta S standard conditions, and that'll give you delta G at standard conditions. If it's non-standard conditions, if it's delta G, then they're going to have to give you delta H minus 2 delta S. These are non-standard conditions because they don't have the not symbol. So in this next section, we're going to look at the relationship between standard Gibbs free energy and just Gibbs free energy changes. And then this last part, which is really important, this is going to tie in equilibrium, what we've been doing in chapters 15, 16, and 17 with chapter 18. So why is it that some equilibriums lie to the right and some lie to the left? Like we said that if K, the equilibrium constant, is much greater than 1, we say the reaction's favored and the products are favored. If K is much less than 1, we said there's not much of a change in equilibrium, not much change in the reactants, and the reaction mostly lies to the on the reactant side. The reactants don't become product. So that's what this is going to do for us. This is going to show us mathematically the relationship between standard Gibbs free energy and equilibrium constants. So we'll see that in the next video.